Okay, so um, today's homework or this week's homework involves the fundamental theorem of calculus. So let's go over what that involves. There's two parts to it. Um, the first part says something about what happens when you take the derivative of an integral. Okay. And so the way we normally see this written is like this: d dx of an integral, the integral going from some constant a to some variable t, and inside the integral we're using a different variable. So, all right. And what Ftc says is that this is equal to f of x. So it's like you take the function inside and you just replace the variable t with the outer variable x. So t is the inner variable, x is the outer variable. Kind of just replace one with the other. There's a generalized version of this, which involves what happens when that upper limit, if instead of that being x, if that's just a function, g of x. And in that case, I should make my f's and t's look a little bit more distinct. Yeah, so, but what happens in that case is this is actually a chain rule. So it's like just like before, we plug the variable limit into the in as our inner variable. So this is f of g of x. We just plug g of x as t. But then the next thing is that we have a chain rule that happens. And so this is what you get. I should make that look a little bit neater. Okay, so both of those are Ftc Part 1, but this is just the generalized form of it. And so really, like, you can see what this is saying is kind of, this is an interaction of how the derivative and the integral work when you like compose one with the other. So you see that derivative and integral kind of cancels out. Okay, now let's see what happens with Ftc Part 2. So it says something kind of different. Integral a to b, f of, this time we don't need a different variable, so we can just say with respect to x. And well, what it's telling us is that we can calculate this as an evaluation using the antiderivative. So this capital F, if you can compute the antiderivative, then you can compute the definite integral by doing that and then just subtracting off. So that's just capital F of V minus capital F of A. And so this is actually the usual way that we calculate these definite integrals, right? Because it definitely beats out what we were doing in the previous homework assignment with the whole Riemann sum kind of approach. With the Riemann sum kind of things, you kind of need to make certain that that summation would converge. Although in the previous homework, we were kind of dealing with easy situations. We weren't considering like letting the limit actually, or dealing with the limit. Instead, we had like these areas under curves that were easy to look at and compute because they were just geometric. You'll actually get into more about the stuff about convergence of series when you take Calc 2, if you do take Calc 2. So that's kind of motivated by this question of how do you calculate a definite integral when you actually can't find this antiderivative? So such things show up in usual kinds of problems. It's just that we sort of give you simpler problems when you start out. Simpler problems, simple enough that you can actually find what the antiderivative actually is. Okay. Yeah. So right, and let me connect this to the first part, because like both parts of Ftc are actually saying something about how does a derivative and integral interact with each other. So, but here the derivative is actually hidden just a little bit. So what we need to do is we need to recast this little f, because notice this is actually defined to be the derivative of the big F. So like if you actually think of this as the integral of I don't know, it's kind of tricky to write this, right? Because you could kind of have like two different things going on. You take the derivative of, oh, no, I don't want the prime in this case. But so yeah, if we kind of think of things not in terms of the little f, but sort of in terms of the big F, then we actually do see that this is actually the integral of a derivative. And then it kind of goes back to the capital function, except with this little caveat of this evaluation. So it's almost like an inverse, but not quite. Okay. So now we're just going to be using these two statements in FTC, and they're very useful. So for number one, all of this is evaluating these definite integrals, which falls under the FTC Part Two kind of case. Okay, so let's go ahead and do it. So just first we figure out what is the antiderivative. And for this one, it's, I think, pretty straightforward. And then you have to evaluate. So evaluate, I'm going to plug E in. I'm going to get 5 times 1 for the first term. For the second, I get a E squared over 2. And then for the second term, I put a big parenthesis because I know I'm subtracting off 2 terms. Okay, so I plug 1 in. Well, that's going to, ln of 1 is going to be 0, so 0, and then plus a half. Okay, and so now this is 5 minus a half, and so that's 10 over 2 minus 1 over 2, so 9 over 2 plus E squared over 2. That's probably the cleanest way to write that. For part B, well, we're going to integrate. So cosine's integral, I think we all know. Sine, for this second term, it's actually helpful to think of it as negative sine, because if you think through your derivatives, you can realize that cosine's derivative is negative sine. So this is actually just going to be 3 cosine of theta, which we then have to evaluate from 0 to pi. Okay. Well, if I plug pi in, notice that the sine is going to be 0, the cosine is going to be -1, so we end up with a -3. Say minus off. Evaluation at 0. So now when we plug in 0, sine is going to be 0, and cosine is going to be +1, so this is going to be a +3. And so in total, this ends up being a -6. Okay. For C, it would be nicer to think of that term in terms of x to some power. So x to the -1/2 power. And we can integrate that. So x is going to turn into a 1/2 power, and then we would normally divide by half. Well, we can reciprocate that, so it's just multiplication by 2. And then we've got a 7x there, and we're evaluating from 4 to 81. Okay. So this is just 10, and I just need to take a square root. Okay, so this ends up being a 90 plus 7 times 81 minus 20 plus 7 times 4, which is a 70 plus 7 times 81 minus 4. So there's a way you can compute this by hand, like minimally, without doing things that are too annoying, but which kind of involved, the way I did it was something like this, but I'm just going to skip to what the actual final answer is, 609. Yeah. Okay. And now for D, well, that 4 you can pull out of the integral. Okay. And then when you do that, hopefully you see that the inside, this 1 over 1 plus x squared, you can think through the derivative rules that you know about, and it should be kind of, with enough practice, it should be immediately clear that this is inverse tangent. So you have inverse tangent function inside, and you want to evaluate this from -1 to 1. Okay. What I'm going to do is I'm going to split that 4 out of the evaluation. That's kind of just like you're factoring 4 out and you're only evaluating the part inside the brackets from -1 to 1. And so now it well boils down to knowing what is inverse tangent of 1. Well, the way you think about this is tangent of what angle is going to give you the value 1. Well, the answer is going to be pi over 4. It's going to be a 45-degree angle. So you end up with pi over 4 for the first evaluation. And then for the second evaluation, it's the same kind of thing. It's what angle is going to give you -1. And I mean, here there's sort of a technicality we have to consider. Like you have to know that the shared screen window is closed. Okay, so OneNote crashed. I think it's back. Okay. So yeah, so it involves knowing what part of what part of the tangent function do we take in order to define the inverse tangent function, the arctangent function. And that's just these 2 quadrants, so the first and the fourth. So the corresponding angle is the -pi over 4. But so this is actually minus negative, right? Because for the second evaluation, you subtract that off. Okay, so well, so that's going to end up being pi over 2. Then you times it by 4, so you get 2 pi. Okay, are there any questions so far?
So can you explain how you went from that to inverse tangent?
Okay, so when you split off the 4, the integral you end up with is, you can write it like this. Okay, so it comes down to pattern matching, seeing this 1 over 1 plus x squared and kind of recalling from the list of inverse trig derivative rules, the arc. So like you should have all those derivative tables somewhere, and you can look through and you'll see like this showing up.
Okay, that makes a lot more sense. Thanks.
Yeah. It's all pattern matching. That yeah. And I'll say like normally textbooks tend to take that dx and put it on top. I think that's just to save space. When I write things out, I usually put the dx off to the side, but they mean the same thing. So having that dx on top is just another notation, I guess. All right. In a way, it's kind of abusive notation. That's the term. It's like you're multiplying the 1 and the dx and getting dx, which is sort of true, but not, doesn't look, I don't know. I don't like it, but textbooks do it. Anyway, right, so part E, power rule, reverse power rule. So we would add 1 to the power there, and so that's going to give me 1/3. Divide by 1/3, same as multiplied by 3. This next term, though, I have to rewrite this. So this is going to be z to the 1/3 power. So when I add 1 to that, I'm going to get 4/3 power, and then times 3/4, which clearly there's a cancellation there. And then we have to do an evaluation from 1 to 64. Okay. So the question is then, what is the cube root of 64? Right, that's what you want to know. And well, you can track that 4 cubed is equal to 64. So there we go. Just have to hope that it's power 2 and check that indeed 4 works. All right, so then this first term is going to give me 12. Then the second one is actually going to give me, so notice I take the cube root, but then I raise it to the fourth power. That's just going to be as though I multiply 64 by 4, and then I would have to multiply it by 3 afterwards. So maybe I'll just say 3 times. And then I can at least multiply 64 by 4, 128, 256. Okay, then subtracting off the evaluation at 1. That's pretty easy. So 3 plus 3, right? So we can at least say that this is minus off 6. 6 plus 3 times 2, 56. And then you have to do some work. I'm just gonna, what did I end up getting? 774. Yeah. So you can see all these arithmetic things, like you could do it if you wanted to. I just don't feel like doing it live. All right. Okay, so that was all number 1. Next we have number 2. And these problems are a little different. Instead of Ftc Part 2, we are now using Ftc Part 1. We have a derivative of an integral. Part A is the easiest case. So the limits 3 to x, all you have to do is you just use the straight up formula that's given to you. Just replace it in. So x replaces the t in function. Maybe I'll put parentheses around that. And so that's it. That's it for part A. For part B, notice that the x is on the bottom. So this doesn't actually fit. Right? This is actually not the same as what the formula requires. It's important that the variable is on top. So what you want to do is actually want to flip the order of the integral. And you know that by flipping the order of the integral, that's going to introduce a negative to the answer. So you could then like just write the answer out, but I'm going to show a little bit more work than I normally would. I'm going to actually show what I just said in words. So I'm going to flip the order of the integral and introduce a negative. All right. Okay. So that's what I said that is what we're doing. And so now when we evaluate this, you see that a negative pops up. Cosine of x cubed. There we go. Okay, and now C is the most complicated example that you'll see happen. So not only are these not just x, but they're functions of x, but you also have two variables. So this is very different. And what you have to do is you have to split the integral so that you introduce a constant into one of the limits. So the way we normally do that is just imagine that you split it around 0, because 0 is the easiest constant to pick. So it's like you divide the region that you're integrating over. That's normally from 7x to x squared. You just plop a number in between there, assume 0 is in between, and just go and do, like this. Okay. And so the first one, you will need to mentally reverse the order. Then you'll have the generalized Ftc Part 1, because this is not just x. This when you take the derivative, you're going to get a 7. And the second thing you have to do, basically the same thing. Okay. So let's, I think we can just go ahead and write the answer. I don't want to like write too many things down. So start off with the negative, because it's going to introduce a negative. And this 7x is going to replace t. So all of t gets replaced with 7x. Sine of 7x, like that. But then remember that you need to put on the chain rule piece. Okay. So that's the first integral that we just wrote down. That's what the derivative of the first integral evaluates to. Next, the derivative of the second integral. So we will take the x squared and plug that in. So we're going to have an x squared sine of x squared like so, and then chain rule, so times 2x. Okay, so that's it for number 2. Questions? No questions. All right, then so number 3 will be our last problem, because otherwise I probably won't have enough to talk about next time. Yeah. So yeah, number 3 has 4 parts, and they all involve this graph. Part A. So okay, first of all, we're defining this capital A function in terms of this v function. It's the integral, so you can think of it as the area under the curve. And first, we just need to plug these values in. So we can kind of think about this in terms of the formula. So notice if I plug 0 in, this is saying it's an integral from 0 to 0. So there's no area to that. I mean, it's like it's a slice with a width of 0. So the area for that would be 0. Now, what about an integral from 0 to -1? Well, so that's going to be this region that I'm pointing out, but it is counted in reverse, right? Because the order of the integral is going in reverse, it would sort of negate the fact that this area would be counted negatively. So we end up just counting this positively. So this is just 1/2 times base times height. So you end up with 2. Okay. For a of 2, so that would be an integral from 0 to 2. Well, this triangle here, that triangle there are going to cancel each other perfectly. So you end up with 0 for that. And then for a of 4, integral from 0 to 4. Well, because 0 to 2 has the integral equal to 0, we can just think of this as being 2 to 4. And so the calculation we need to do is 1/2 times 2 times 4, which is going to be 4. Okay. Now for B, so this derivative, the way you normally would do this is you would take the derivative of the a function and then you plug into, that's the order of these two things in this statement. Well, that we're going to end up taking the derivative of an integral. So hopefully you can see what we need to do. I'm going to spell it out though. So I'm going to say a prime of x is d dx 0 to x v of t dt. Okay, and so this should remind you of Ftc Part 1, and that is actually equal to v of x. So a prime, the derivative of the a function, is just a v of x function. Okay, so if we plug in 2 to this new function, or old function, that's the same as plugging into the v function. So all we have to do is just read the height off of the graph. And so answer is 4. Okay. Maybe I should box it. Okay. So now C is a good problem, I suppose, because it would throw some people off. So when is A increasing? When is A decreasing? Well, the thing is to know that the statement about increasing and decreasing is really a statement about the derivative of the function. Right. So A increasing, what it means is that the derivative of A is greater than 0, right? But that the derivative of A is just the same thing as v of x. So you don't need to write that. I'm just sort of explaining the thinking process. So yeah, A is increasing when this graph is actually positive. So that's minus infinity to -1 and 1 to 4. I'm just going to write that down. Minus infinity to -1, union 1 to 4. And a of x decreasing, well, it's the same idea, so you can fill in the dots. But I'm just gonna take the complement of this interval. So -1 to 1 union 4 to infinity. So that's when the v function is negative. Which you can see -1 to 1 and 4 to infinity. Okay. Right. Now for D, suppose that S is a position of a particle, S prime is V. If S of 0 is 5, find the position at time 4. So find S of 4. Well, the thing that would relate S of 4 and S of 0 to each other would be it would be this kind of calculation. It would be Ftc Part 2. So the integral 0 to 4 of, and then in this case, well, you could write this as the S prime function, but really we know that this is the V function, right? So the only thing that you need to check, I guess, well, you don't even really need to check anything, but like in the statement of Ftc Part 2, what it says is that the thing on this end is always the capital function, and the thing inside it is the lowercase. So like normally, I wrote it up here, right? Little f and big F. So the integral of the little f is the subtraction of two big F's. But the statement that is assumed is this relationship that the derivative of the capital is equal to the lowercase function. So this is guaranteed to us by just the way that the problem is stated, but that's always how these things are related. So yeah, you can see that the capital would be the outer, which is the S. Yeah, and its derivative is the V. Okay. Then the thing is, how would we calculate this integral? Well, it's visual. So 0 to 4, which you should actually recall is something you already calculated here. It's this A of 4. So that's just the value 4. And S of 0 is given to us. So we can conclude that this is going to be 4 plus 5, which is going to be 9. And we should put units at the end. So 9 feet. Okay. Yeah, any questions on anything? So, if there aren't any questions, then we'll end here, and we'll continue next time.